Usually it's just you.
Yeah, it's usually just Dennis. Yeah.
Wow. I guess I'm the one asynchronous with me.
I mean, a mix of people, like people like, well, Rhiannon, you told me that you like to watch the videos. Yeah. But I mean, it's just, I let students take it however they want, you know, synchronous Zoom, in person, asynchronous. I mean, whatever, however they want to do it. But no, it's interesting. The university thought that there would be like a huge rush to go back in the classroom, and we're just not seeing it. Like students like being online.
Same thing for like working too, right?
Yeah. Well, I was telling Dennis before, I had a meeting this morning, 7 a.m. I was talking to Lapster, and it was, me in Hawaii. There was someone in Brazil and someone in Copenhagen, Denmark. So, like that's just society now, it's just in like, I mean, it's also good for, someone like Maui. I mean, like, here we are, here I am in Maui doing business, in Europe. And I mean, it's, in real time. So, but anyways, I guess we better start. Final day of class. Ooh, does anybody know what today is? It's a nerd holiday. I'll give you a hint.
Star Wars.
Yes.
The 4th.
May the 4th be with you. And I am wearing a Wookiee t-shirt. And I am definitely going to watch one of the Star Wars tonight. You should watch Star Wars tonight, you're saying? Yeah. So may the 4th be with you. With that in mind, before we start, does anybody have any questions about anything on today? Ask what we're going to today. I'm just going to go over problems and kind of review for the final. Of the most, it's going to be the first part. I looked over the final again, and like I mean, 50 problems, multiple choice, but they're of the simpler kind. I mean, yes, you do have some of the problems, like, I mean, where you have to solve for the logarithms, but I did one of those, like, it's, like the Clausius-Clapeyron, kind of thing. That's the vapor pressure, problem, and other problems like, what is that? The Arrhenius equation in kinetics. I mean, it's just similar kind of stuff, but that's probably the more math complicated ones. A lot of them I mean, if there's 50 questions, come on now, I'm not making you sit through a 6-hour exam. They're going to be easy questions. The target for it is 2 hours, although I guess it's about 2 hours. Although you can take as long as you want. I don't put time limits on things. So the problems aren't going to be that hard. I mean, like well, depends on I guess, in a matter of opinion there. But if you notice that in the tests, I put some of the word problems, and those are a little harder. So you're not going to see any of that on the final. So, and also unofficially, students that score higher on the final, they get the score they get in the final. And although the vast majority of students, like on the order of 75-80%, score exactly the same in the final as they do in the semester. So, but 10 to 15% students, like say they're scoring B's in the semester and they get an A in the final, I give then they get an A in the class, because final is comprehensive. And I mean, I think there's something to be said, especially students that improve, throughout the semester, right? I mean, because I want to reward you guys for putting things together at the end. Of course, the students that are doing A level, keep on doing A level, because the final can bring you down. So, but that rarely happens. I mean, probably only like 2 or 3% of the students, less than 5% of the students score worse in the final than they do in the tests. So that's good. And okay. Does anybody have any questions about final or anything like that? No. Okay. So moving forward, I guess I better share the screen. And open the chat. Okay. All right. So again, picking up on the review. So this is connecting standard Gibbs energy with the equilibrium constant. So use the free energies to calculate the equilibrium constant for this reaction at 298 Kelvin. And it's N2O4 in equilibrium with two NO2s. So first things first, we got to get the delta G. Delta G0 reaction is the sum of the N of the products, G of the products, minus the sum of the N of the reactants. G of the reactants is going to be equal to products 2 G0 F NO2 minus G0 F N2O2 equals 2 times 51.3 minus 99.8. And so what is that going to be? Is that going to be, is that just 3? I think it's just 3 kilojoules. No, I'm wrong. According to the book, it says 2.8. All right, we'll go with the, is that right? Someone's looking at this. This is, oh, because there's 2 of that. Okay. Okay. 2.8 kilojoules. Okay. And so that's the delta G reaction. And looking up there, the equilibrium constant is going to be E to the minus delta G0 over RT. So I always write it out longhand, minus 2800 joules. It's 8.314 joules per mole Kelvin, temperature 298 Kelvin. And what is that going to be? That's E to the minus 1.13 equals 0.32. And there's the answer. So recap for this one. So using this equation, standard Gibbs free energy change equals minus R, which is a gas law constant, times temperature times the natural log of equilibrium constant. Solve for equilibrium constant, it's going to be E to the minus delta G over RT. And then, so from this, we got to figure out what delta G is. So do the sum of moles of products, G of products, free energy of products minus moles of reactants, free energy of reactants. Do that, get 2.8 kilojoules, and then put the 2.8 kilojoules into the equation and get 0.32 as the equilibrium constant. So questions with this one? Okay. Some of my favorite ones, students don't like this as much. Half reactions. So solve this in acid. And so we have the equation here, iron plus 2 plus MnO4 minus yields iron plus 3 plus Mn plus 2. We need to figure out what the oxidation state is for manganese and permanganate. So -1 equals manganese's oxidation state plus 4 times oxygens. And I'm getting that because there's the charge -1, and there's 1 manganese and 4 oxygens there. So oxygen tends to be -2, -1 equals manganese plus 4 times -2. So then 4 times -2 is -8, add to both sides, 7 is manganese. Man, I'm hyper. I'm just thinking about it. I knew I was gonna do a lot of math today, so I ate a lot of I ate a lot of sugar for breakfast, and man, I feel the buzz and the energy. So that's +7. So we do then we look at the half reactions. So MnO4 minus +5 electrons makes Mn +2. And I know this is myself, I do it slightly different than the book. But I mean, at least as far as half reactions, they do it the same way. And then iron +2 yielding iron +3 plus an electron. So we consume 5 electrons with permanganate and we generate 1 electron with iron. So we need to multiply this by 5 to both consume and generate 5 electrons. So we put 5 here. So then you have to balance the oxygens. So on the left side of the equation, there are 4 oxygens. So we need 4 waters to balance off the 4 oxygens. Now we balance the hydrogens. There are 8 hydrogens on this side. So we need 8 hydrogens on this side. And we're done. Yeah. Which, can you tell me? Okay, this is figure out the oxidation states. Yeah. Yeah, you have to look to go back to 161 and see my old notes. I think it's chapter 5. Yes. Yes, but is it 4? Oxidation states. Where is the oxidation states? Do you remember doing the oxidation states? Oh, here they are. Yeah, here we go. Yeah, but you must have done the signing oxidation states to do the oxidation reduction reactions, right? Or you haven't done that in your, because yes, but you've written me about chapter whatever 19 homework.
Yes.
So you must know how to do it, or
Yeah, it was, I think I just did it.
okay, that's fine.
But you really seems kind of easier.
The book does it differently.
Right, and also like on the electric chemistry one.
Yeah. 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 Of course, my method is better. How dare you even question that? I'm kidding, of course. But no, that's this is all the way back here. What I was doing there, and if you see this chart, like the rules for assigning oxidation states, and they're hierarchical, and one of them was the oxidation state is the equal to charge. It's like iron +2, iron +3. Those are the charge, and then the sum of oxidation states of an ion equals charge. That's where -1 is permanganates, and like and then when I was assigning states, you go down to this chart, and oxygen tends to be -2. So that's what I was doing with. Oh, wrong. There we go. Oops. That's what I was doing there. I was using the oxidation state rules to figure out the oxidation state of permanganate, or of manganese and permanganate. Other questions? Okay. All right, and now using the Nernst equation, determine the cell potential for the cells based on the half reactions here. So this one you have to use the the Nernst equation where the E cell is going to be the standard E cell minus 0.0592 volts divided by the number of moles of electron times times the log of Q, the reaction quotient. So I guess best thing to do would be balance. I guess even before that, I can do E0. So E0 cell is, it's going to be 1.68 plus or minus 0.34. So that's going to be 1.34 volts. And I've gone ahead and looked these up on the table. So the reduction potential is 0.34 volts for this one, but since it's the oxidation, it's going to be opposite the reduction potential. And this is just written as is. So then let's look at the equation. So there's 2 electrons being generated and 3 being consumed. So we're going to multiply the top one by 3 and the bottom one by 2. So it's going to be 3 coppers plus 2 MnO4. I'll put the states in, so I'm sloppy. Copper solid plus 2 MnO4 minus aqueous plus 8 acids aqueous yields 3 copper plus 2 aqueous plus 2 MnO2 solid plus 4 H2O liquid. Okay. And I'm doing that to show you the Q. Q is going to be products over reactants. It's going to be copper plus 2 cubed over MnO4 minus squared acid to the 8th. So because you do not include the solids and liquids in the equilibrium expressions or reaction quotients, only the gases and aqueous. So because liquids and solids have constant concentrations, or near constant concentrations, I should say. So, okay. So now we apply this equation. So the Nernst equation, so that means this is 1.34 minus 0.592 volts over 6, because we have 6 moles of electrons we're transferring. Log of copper plus 2.01 cubed over 2 squared 1 to the 8th. And thank goodness acid is to the 1 molar, right? That would make this problem harder. And you do all that and you get 1.41 volts. Let's just put volts here. So, all right. Anybody have any questions for the setup for this one? Although we just covered this, so hopefully you follow it. Okay. Okay, question. How do you determine which element is oxidized and which one is reduced? So for this one, it tells you that you have the oxidation and the reduction. So how do you know which one? It's if you look at the standard cell potentials, the the one that's higher up is going to be reduced, and the one that's lower is going to be oxidized. So let me pull up that, no, it's 18, 19B. Let me pull up the chart. Yeah, the one further down. Yeah. Here we go. Here's a chart. So very messy chart. So the standard cell potentials here. So standard cell potentials and the reduction potentials. So let's say you have two elements. You have, I'm picking silver and I don't know, lead. So silver and lead, and which one of these two is going to be oxidized and which one's going to be reduced. So the higher up one will be reduced and the lower one will be oxidized. And the reason for this is that doing it this way, you get a positive E0, and that means a negative gives free energy. A negative gives free energy is spontaneous. And why do we have positive for electrochemistry and negative for thermodynamics? It's because the two branches were developed independently of each other. And when maybe you started to notice that, you're like, in electrochem, they use H+, and in acids, they use H3O+. So the branches were developed independently of each other. And although I personally tend to use H+, you know, if you notice that the book tends to use H3O+, except for electrochemistry, but I tended to be a little more consistent and use H+, but you know, they both work. So, but hopefully that's answering your questions. Yeah, other questions? Okay. I got the nod of approval, so it means I will move on. So this is stuff unique for today. And this was a request to go over this problem. Determine the hydroxide ion concentration of a solution that is 0.13 molar in carbonate. So to do this, the first thing you have to do is write the hydrolysis reaction. So to write out carbonate, that's aqueous, plus water is in equilibrium. This is called the hydrolysis bicarbonate. So that this is known as the hydrolysis reaction. So reaction with water. And then do initial change equilibrium. Initially, this is going to be 0.13. This is going to be 0, 0. Liquids doesn't change. Change, we're going to lose an extent of reaction. And so it's going to be 0.13 minus x, x, x. And then we have, so our KB is going to be bicarbonate. Hydroxide all over carbonate. And we know it's going to be 1.8 times 10 to the minus 4 times or equals x squared over 0.13 minus x. And you can use the x, the small approximation, x squared over 0.13. And then that means, so x squared equals 0.13 times 1.8 times 10 to the minus 4. Take the square root of both sides. And then doing that will give you the hydroxide ion concentration. Did you want me to actually carry out the math, or are you okay with the setup? I think that if anybody wants me to do the arithmetic, let me know. I can always do that. So, but I think the more important thing is to see the setup. Questions, I guess.
I forgot how the salts associated. So you have like a strong. What if you have like a salt that's connected to base and strong?
Acid? Yeah, okay.
How does it associate?
So a weak base plus a strong acid. Okay, so in this case, you're going to get an acid salt. So easy thing to remember for salts, your strong bases are lithium, sodium, potassium, rubidium, cesium, very infrequently, but beryllium, magnesium, calcium, strontium, barium. So the alkali is an alkaline earths, and the word alkaline means basic, right? So these are strong bases, and our strong acids are going to be HCl, HBr, HI, HNO3, HClO4, H2SO4, but not HSO4 minus. So the ions, so think of it this way, the ions that are not going to react with water, so I'm too hyper today, will not react with water. It's going to be, for acids, Cl minus, Br minus, I minus, NO3 minus, ClO4 minus. On the acid side, basis side, lithium, sodium, potassium, rubidium, cesium, beryllium that we don't use, magnesium, calcium, strontium, and barium, which means every single other ion is going to react with water. Okay, and if it's a weak acid, it's going to react to form an acid plus hydroxide. If it's a weak base, it's going to form oh no, it's going to be HB. It's not going to be B minus. If it's a weak base, it's going to form an acid. Oh, geez. It's going to form an acidic environment. So that's the real reason. If you like my logic, think strong acid, weak base. Strong acid, weak base, acid salt. Or strong base, weak acid, basic salt. So the stronger one wins. So, but the real reason is the reactions with water. Oh, so if an acid salt, okay. So like say it just doesn't react. So Cl minus plus water is no reaction, right? So like if you have NaCl solid plus water, it forms sodium plus aqueous plus Cl minus aqueous. But if you put sodium, okay, acetate, this is going to form, okay, I don't have enough space for this. So if I have sodium acetate in water, that's going to form, well, sodium plus OH minus plus acetic acid. So right, you take sodium acetate and you throw it into water, it forms hydroxide, sodium ions, hydroxide. A lot of times we don't even include the sodium ions, we just say acetate and ion. But yeah, because the sodium essentially becomes a spectator ion, and sodium, it just doesn't react with water. The counter ions of the alkalis and alkaline earths are not going to react. Yeah, question. Because they've already given up their electron. So they've given up their electron and they have the noble gas configuration. So they're very, very stable. And if you compare it to, I mean, something like aluminum though, it's aluminum forms a water complex. So, and then the water then can, then from that, it can protonate and deprotonate from the complex. Let's just say it's just a deprotonate. It'll react, then the whole complex then reacts. So, but I guess the short answer is the electronic configuration and the size of the ions are such that they don't appreciably draw water around themselves in solution. So from that, you don't get a delocalized weakening of the oxygen hydrogen bond in a ligand in the ion with the stuff around it, with the water around it. So, but because of the size of the ion and the stability of it, it just does not form that complex, whereas other metal centers do. Oh, I should say other water soluble metal complexes do. Are you just talking about the metals, or do you mean? Yeah. Because mostly from the ion size and stability of the electronic structure in cloud. And because of that, it just does not form covalent bonds with water. So, good question. You're always asking me the advanced questions, which is great. Not on the final though. You don't have to know about the relative, ability of ions to form covalent bonds with water. So you will though if you become a chemistry major, although most people don't. Any other questions though? Okay. So, and I'm trying to, I was just looking for the final and I was thinking about you guys as students, and I wanted to go over the earlier stuff because it's probably exited your minds. So I am trying to refresh you on these. And I also, from a student's perspective, whenever I got easy questions wrong, I would be so mad at myself. And like, so get the easy questions right and the hard ones wrong, or, not really, but, don't get the easy ones wrong, because those are those are the easiest points to get. The point to effort ratio is low. So, and this is going back to intermolecular forces. So this problem here, so place the following substances in order of decreasing boiling point. So these elements here, they're all going to have dispersion. So this is dispersion only. So, right, if you remember the strengths, so we have London dispersion and London forces, dispersion forces only, then dipole, then hydrogen bond, then ion, oh, too many I's. Ion dipole. So strong. So as you go down. So, and with dispersion, you have size, and in general, size goes up, the bond goes up. So the bigger the molecule, or the heavier the molecule, the bigger the molecule, the more the bigger electronic cloud, the easier it is for the electronic cloud to polarize, to move. And the other thing with dispersion, which I don't, just for completeness, but it's also the shape. The closer to a sphere that the molecule is, the less likely it is to polarize. The more surface area, like a flatter molecule, is going to have more polarizability. But for this level, looking at the final, it's really just going to be the size. And so oxygen, this is going to be 32 grams per mole. This is going to be 35.4, 70.9 grams per mole. And hydrogen is 2 grams per mole. So those are the masses. That's a 2. So from this, so it's order of decreasing. So chlorine is going to be the highest, and that's going to be higher than oxygen, higher than hydrogen. So order of decreasing, going down. So, but with the intermolecular forces, so boiling point is higher with the force. Yes, May the 4th. The force, the strength of the bond between them. So the intermolecular forces, the stronger the intermolecular forces, the higher the boiling point. So the water in my water bottle compared to the plastic in my Apple Pencil, the forces in the Apple Pencil are stronger than the forces in the water. Okay, so therefore, the Apple Pencil plastic, I think this is polyethylene. The polyethylene here is going to have a higher boiling point than water, right? So because the bonding is stronger here. And then other things that go up, viscosity. Viscosity goes up with the force as well. So viscosity is resistance to flow. So that means that, okay, well, something that has a stronger intermolecular force. So ethylene glycol, antifreeze. Ethylene glycol is going to have a higher amount of intermolecular forces than water. So that means that the viscosity of antifreeze is going to be higher than the viscosity of water. So, or something that has a lower intermolecular forces. So gasoline is going to have a lower intermolecular forces than water. Gasoline is going to have a lower viscosity. So if you're ever to swim in gasoline, which I recommend you don't, it's going to it's going to be less viscous than swimming in water. So viscosity means resistance to flow. It's from the density, but yeah, you would sink faster because the density is about 80% that of water. So in my daydreams, I've sometimes wondered what it would be like to be on the moon of Titan and Saturn's moon Titan, because there are oceans of what do you call that stuff? Ethane. And so, I mean, if you were in your spacesuit, you would sink in that. But the gravity is so light, though. If you had a big enough wings, you could flap your arms and you could like fly in Titan, because the atmosphere is thicker than here on Earth, and even more so if you were swimming. So I don't know, weird random thoughts that I've had. But yeah, no, you don't want to swim in gasoline. You wouldn't be able to stay floating unless you had like a flotation, unless you had some air or tires or something like that to keep you afloat. You go right to the bottom. So, other questions? Okay, so yeah, so I just if you remember back to chapter 12, when you have the intermolecular forces, there'll be things like boiling point, viscosity, that kind of thing, and trying to relate them to the strengths. So, oh, and also with that, if you have dissimilar molecules, the London dispersion forces only are going to be the weakest. Follow them by dipoles, followed by hydrogen bonding. Hydrogen bond is when you have a hydrogen directly attached to a fluorine, oxygen, or nitrogen, and then ion dipole. So it's just ranking the different molecules in terms of something like boiling point or something like that. So, and pay attention to the logic, decreasing, increasing, that kind of thing. So, questions with this? Okay. All right. Heating curve. Enthalpy change for converting 10 grams of ice at negative 25 degrees Celsius to water at 60 degrees Celsius is blank. So I always draw a little picture. So we have ice at minus 25 degrees Celsius, and you heat it up to the melt. And then you have water or liquid. It's always H2O. Liquid at 60 degrees Celsius. So you have three steps. Oops. So the first one is going to be Q is mass times specific heat of ice, delta T. 2 is moles times heat of fusion. And 3 is Q, the heat, Q is the heat. And they're all heat. Heat is equal to mass specific heat of the liquid, delta T. So 1 is equal to mass 10 grams, specific heat of ice, 2.09 joules per gram. Kelvin is the same thing as unit-wise as Celsius. Delta T is 25 Kelvin, Celsius, however you want to put it. The second one, it's going to be 10 grams water times mole water, 18 grams water times heat of fusion, 6.01 times 10 to the 3 joules per mole water. And I'm trying to hint you to see what the most common mistake is. The kilojoules. Don't forget that that's in joules and that's in kilojoules. And then 3 is 10 grams times 4.18 joules per gram Kelvin, 60 Kelvin. And I'm also stating you probably can assume, I'm hoping everyone knows that water melts at 0 degrees Celsius. So that's the other thing that's kind of assumed that you know. So of course this test is open book, so you can look up the freezing point of water if you forget it. But it's one of the easier ones. So is this okay, or do you want me to do the arithmetic? I can tell you the answer. It's D. You already can see that. But questions with this one? Yeah. So that one's a lot of arithmetic, but don't get that one wrong. So in Henry's law, if you've forgotten this, Henry's law is solubility equals the Henry's law constant times the pressure. So, and so this is a straightforward one. Solubility, going to be Henry's law constant, 3.7 times 10 to the minus 4 molar per atmosphere times the pressure, which is 0.4 atm. So that's about right. It's about 15. Yep. So this one is just a straightforward across, look at the units and one step reaction or one step solution. So, but questions on how to do this one? Hopefully it's all okay. You all right, Dennis? You thinking, or you're just? Yeah, no, I'm trying to read your mind or read your facial expression. Yeah. No, do you have a question? I'm not trying to pick on you. Do you have a question or? Okay. Yeah. It's just hopefully you're just like, oh yeah, well, you learned all that crap, you know, not crap, this wonderful material. Yeah, question. Yeah. Yes. Yeah, originally we're looking at 25 degrees Celsius, but yes, you change it from that. But the other thing with Henry's law constant, it's a semi-empirical model where they just take all of the variables and put it into a lump sum approximation. And so this constant is just, they don't even bother learning it. They just like, all right, we'll just take data at a bunch of different temperatures and then tabulate it and then, you know, just deal with it that way. But you don't want to be an engineer, do you? Or are you going to be an engineer? Okay, engineers do this all the time. You see this in so many things: heat transfer coefficients, I love efficiency coefficients. Like, we don't know what's going on, but we know it works this way. So we're just going to take a bunch of data and tabulate it. So yeah, sorry, I'm talking about random things, but yes, change of the temperature. So, all right, moving on then. A solution is prepared by dissolving 91.7 grams of fructose and 545 grams of water. Determine the mole fraction of fructose if the final solution is so much. Is that also with this, you don't even need that information. That's extra information. That's just there to confuse you. So the mole fraction is just the moles of something over the total moles. And the moles of fructose, so it's going to be 91.7 grams fructose over 180 grams fructose divided by 91.7 divided by 180 plus 545 grams water over 18 grams per mole. So, and I know you need the units there, but I'm just leaving them out. Did you want me to do the arithmetic for this one? So, and don't forget also when you deal with colligative properties. So many times like Raoult's law, where you have the vapor pressure is the initial vapor pressure times the mole fraction. So you might have a problem like that, and then you have to calculate the mole fraction from that. I didn't have a problem like that in the test, but I think I specifically have a Raoult's law on the final, if I remember correctly, when I was looking through it. So, but questions? No questions. All right. You remember everything. Hooray. Okay, so determine the boiling point of solution that contains 70.6 grams of naphthalene dissolved in 7 to 22 milliliters of benzene. Pure benzene has a boiling point of 80.1 degrees Celsius and a KB of 2.53 degrees Celsius per mole. So in order to calculate the change in boiling point, it's going to be your molality times the KB, the boiling point elevation constant. And so you got to figure out the molality. So it's moles per kilogram. And I guess it's easiest to do the kilograms of benzene first. So why did that do that? So 722 milliliters of benzene times, grams over 0.88. Oh, no, I'm sorry, the grams are on the top. 0.877 grams benzene per milliliter benzene, and then kilogram to 1,000 grams. So let me do that. This one I have to do the math. This is going to be 0.633. How many sig figs? Okay, 3 kilograms. So then M is moles per kilogram. So it's going to be 70.6 divided by 128.16 divided by 0.633. This equals this equals 0.871. No, 87. Not one, just 0.870. So how are we doing? So then the delta TB is molal 0.87 times 2.53 equals 2.2 degrees Celsius. Now, then the You can see that's an answer choice, but that's there to throw you off. The pure benzene has a boiling point of 80.1, so it's going to be 80.1 degrees Celsius plus 2.2 degrees Celsius equals 82.3 degrees Celsius. So this is the answer there. So that's when you're dealing with the boiling point elevation, freezing point depression, the unfortunate most common mistake is forgetting to add or subtract add the elevation, subtract the depression at the end. So you've done all the hard stuff correctly and then throw you off at the end. So does anybody have any questions with this one? So remember how to do all that. Oh, and I'm actually done. I thought I was going to take longer. I was like, oh, I thought I was gonna, I even had a contingency plan. My plan was I was going to continue teaching and letting you guys go and record the video so you could watch it after. So it looks like we're 15 minutes early. So does anybody have any questions about anything you want to ask or any problems you want to go over? We got 15 minutes, 16 minutes. No questions? Okay. Yeah. And, but like, no, I was thinking about that and I was looking at the exam and I was thinking about how you guys would feel as students, and like, you're like, oh crap, all that stuff in the beginning of the semester. So that's why I was going over it. But like a lot of stuff flows together. I mean, I covered some of the stuff in kinetics last class, and then that's, but then the natural log stuff, it's all the same, right? I mean, you have that the natural log stuff, carries through the entire semester. So if you know how to do one problem, you know how to do them all. And then I'm glad you asked about the acids and bases. That's another concept that people talk about. And I mean, there's not very much of nuclear science in the final. And the stuff it's easy. It's just the types of radiation and balancing equations. I don't do any mass defect on there. So, and the electrochem should all be fresh in your mind, and equilibrium you've been carrying through, so that's fresh in your mind. So that's why I wanted to go over this stuff. So, but
We had a conversation about disputes.
yeah.
What means do you?
It's whatever's there. I just put in. Yeah. Yeah, I know. And we had that conversation. It makes me wonder myself, I mean, like, because the way you did it makes more, wise makes more sense. Yeah. And yeah. And like, I mean, there's got to be some sort of semi-empirical model to it though, because like, if you think of this equation, I mean, we know it works, but something like the delta G0 is RT ln K. I mean, what's so special about 25 degrees Celsius, and moles, standard moles? I mean, why does that work out just for that temperature, kind of thing? So there's got to be some sort of, semi-empirical sort of, error. Yeah, we always use it for 25, but why? But I guess I mean, if you change the temperature, you change the Gibbs energy, but I mean, like, what happens when you're trying to find the equilibrium constant at some other temperature, So, yeah, there's got to be, yeah. I mean, I know how to use the equations and, but I don't have all the mysteries figured out. So, yeah, no, I mean, it's interesting that you wrote me and we talked about it, because it's something I thought about myself. Because I mean, the thing that always bothered me also was when you had the e to the delta g's, or the well, when you raise the e to the power, and I mean, sometimes the units are not right. When you have the equations, the units don't always work out, and then like, because it's especially the moles, right? And when you do that, you just kind of have to drop the unit of the moles when you do those equations. So, because otherwise, like then you get e to the mole squared or something like that, and I'm like, well, what do you do with that unit, kind of thing. So that's the one that always bothered me. And the other thing with thermo, I mean, like everything else, we have efficiencies that we give it. So like, we know it's supposed to be this way, but how it really is, like the math says this, like, and the measured value says this, like, all right, but if we multiply this by 11.3%, it turns out to be exactly true. So we're going to call that the activity coefficient. So we have fudge factor. We call it also a fudge factor. You answer, you multiply to make it work out. So they're all over science and mostly engineering. So other questions? I guess how about you Zoomers? Any questions? Last class. Okay. I'm going to go ahead and stop class 11 minutes early then. And I'll hang out if you guys have any questions. So I don't have any cavities, by the way. Went to the dentist on Monday. But I hate the dentist. It's always, I just don't enjoy it. I'll stop recording.